So I'm going to take the remainder of this time and share some preliminary results from a project, a belt-wide project that we have on refining the heat unit system, the DD60 system. And I want to start with some basic concepts. I want to define what we're talking about with this heat unit model and tell you a little bit about the history of it. The underlying assumption here is that plant growth and development is driven by environmental conditions. And first and foremost, the main parameter would be temperature, right? If we think about our response to temperature, we typically see a logistic growth curve. So if temperature is low, our growth rate is going to be relatively low. As temperature increases, we increase at an exponential rate, and we get to some point, 86 degrees, 90 degrees, and growth starts to slow down, right? So this is the basic premise for the DD60 measurement. Temperature is the dominant factor. Now for humid regions, we typically calculate using minimum temperature for the day and maximum temperature for the day. That's it. We add the two together, divide by 2, we use a base temperature of 60, and that gives us our DD60s. I mean, everybody here probably understands how that concept works. A lot of times you'll hear this degree day 60s referred to as DD60s. Sometimes you'll hear it referred to as heat units or heat units after planning. But this is the system that we pretty well use in the humid Mid-South. That works well in humid environments when your temperature swings are fairly small. When we're going from, let's say, 75 degrees to 95 degrees. But when you get into more arid regions, we spend more time in the temperature extremes. And in that environment, we typically see a different approach. We don't use that daily averaging. We would force a sine curve between the minimum and the maximum. And instead of using that average to calculate DD60s, we'd actually look at area under the curve. Now, that helps us do a better job of predicting growth and development, but it doesn't get us all the way. We still have issues when we get into 100-degree temperatures and we run out of moisture, right? So in addition to running the sine curve, we also see the use of an upper threshold. And in the standard DD60 calculation that we typically use, we don't use that. We don't account for that. There's a lot of different ways to account for that upper threshold, but the most common way is to use just a straight horizontal cutoff where temperature is capped, the area under the curve above that upper threshold is not considered to contribute to growth and development. We just throw those heat units per se out. Now this simple DD60 system that we use now was really settled on in 1983. Extension cotton specialists met and decided from here on we'll just stick with the 60 base, basically use an average temperature approach to calculate it. Prior to this, and there's a lot of conversation from what I can tell at the Beltwide conferences based on the proceedings in the late 70s, early 80s about other approaches. Maybe we should use different base temperatures, different ways to calculate, possibly consider that upper threshold. But SUPAC summarized most of this work, and again, in '83, cotton specialists basically reviewed what they had up to that point and said, let's try to proceed. They developed some guidelines at that point on heat units required to reach key growth stages and settled with that DD60 calculation. Now, since then, there have been several approaches to redefine the heat units it takes to reach a given growth stage, and there have been alternative approaches. So that sine approach that I mentioned just a couple slides back, that came out of Arizona. Arizona uses an 86-55 heat unit after planning approach. They force a sine curve. You won't hear extension specialists in Arizona talk about DD60s. They're going to talk about this 86-55. And that method really developed after they started modeling pink bollworm emergence with their weather stations. So we're not. This isn't something you're going to do on a turn row, right? This is going to be more complex complication, and that's the method that they typically use in Arizona. So we've got a lot of issues with this straight average single lower threshold approach. Plant growth and development is not driven by temperature alone. I just talked about all the other parameters that could potentially influence growth and development, water stress, nutrient deficiencies. A big one that I would like to look at, solar radiation. You know, all of these things can drive growth and development. We also know that response to temperature is not linear, right? And that is the number one assumption here with the DD60 is that the response would be linear. We know it's not. We have this curvilinear approach to plant growth, the relationship between plant growth and temperature. And we're using a constant lower temperature. So our 60 is our base temperature, whether it be May 1st or if it's October 1st. And I would argue that we can probably tolerate more cold stress late in the year than we can tolerate earlier in the year. So there's probably some opportunities to increase the relationship between growth and development and heat units by varying this lower threshold. And as I mentioned, we're not using an upper threshold. There's absolutely no benefit to temperatures at 100 degrees Fahrenheit. We know based on some physiological work that 86 is about the right temperature for a cotton plant to reach that maximum. Beyond that point, we're probably not advancing growth and development. We may actually be hurting us. So, the question is it time to reevaluate? Let's think critically about this. We settled on DD60s in 1983. In 1983, Matt introduced what I believe was called the Lisa computer. I'll get a few nods in the audience. All right, so this was a 1 megabyte RAM computer. Our base Mac right now is 8 gigabytes, which would be 8,000 times the computing power, right? So we've had some massive technological advances over the past 36 years. Think about lint yield from 1983 until today. 1983, this is average lint yield per acre in Tennessee. In 83, we were sitting somewhere around 500 pounds per acre. Past 5 years, we've broken 1,100 pounds for the state, right? So not only do we have more computing power, we also have a very different plant today than we had in the early 80s. I think it's time, in my opinion, to reevaluate these guidelines, if not potentially reevaluate this calculation. There's been several comments, discussions about these higher yielding cultivars may be reaching a couple of these growth stages a little bit earlier, and they may be moving from growth stage to growth stage. They may reach squaring a little faster than they did previously, and they may go from squaring to flower a little faster than historically. And I don't know, Dr. Borland, if you would agree with some of these or not, but I'm really looking forward to getting your input here. A lot of observations in the year. When we start slicing bowls, none above crack bowl 4 and 5, that used to be the standard guideline on you're safe to defoliate. It seems like now we might be safe to defoliate around 5 to 6. Those uppermosts appear to be maturing a little faster than they used to. And just observation. Is the base 60 appropriate? Is an upper threshold appropriate? Do we need to change these throughout the year? Lots of questions to answer on the potential refinement. I think we also have an opportunity to look at a novel approach. With this additional computing power, and not only computing power, but access to better weather data, extrapolated weather data, I think we could pull other parameters in, something like solar radiation or percent cloud cover. We could pull humidity in. These stations weren't as easy to access in the early 80s. Much easier to access now, and we all have access to them with a smartphone. We could develop some type of a calculation and really strengthen the relationship between our predicted growth stage and actual growth stage in the field. So this idea really started with conversations with Jared Whitaker in 2016. We started designing a trial in 2017. We executed a trial very similar to the one I'm about to describe to you in 2017. An approach Cotton incorporated with it. Dr. Bob Nichols worked with us as a group of cotton specialists, and I'm very happy to report that we have over 30 site years worth of data collected at this point. I'm going to share with you some preliminary data from 18, a little bit from 19. 2020 will be a year that we hopefully can complete all of the analysis. One other person I want to mention that has been really important in this whole plan, Dr. D. Tion is a climatologist we've got from Auburn. While I helped manage the collection of all of the data, the plant data, D. Tion summarized all the climatological data and is going to help us potentially develop this new index or evaluate the current index that we have. So, we'll touch on trial design. This was a small plot replicated trial. We had 3 varieties. An early in Delta Pine 1612, a mid in Delta Pine 1646, and a full maturing variety in Delta Pine 1851. Full replications, typically 2-row. Some of these measurements were taken in official variety trials. Most of the time it was its own 4-row plot, and we have these scattered throughout the belt. I mean, we're going all the way from California up through Virginia. So tremendous amount of data. Could not have been able to collect near this data if we didn't have the full support of all the cotton specialists across the belt. This was an extremely time-consuming trial. So every 5 days, we're measuring each plot to determine which growth stage that plot would be in. So spending a tremendous amount of time. The 6 critical growth stages that we established were emergence, first week of squaring, first week of flower, cutout, first week of cracked bowl, and 60% open. So basically twice a week we had these plots. Someone was in each one of these plots. Tremendous amount of data collected with each of these locations. We spent a lot of time developing a worksheet to be able to summarize the data. And the reason I wanted to show this, the goal, we knew with confidence that we were not going to be present when every plot reached each key growth stage. Our goal was to collect a little data before we reached the growth stage, a little data hopefully when we're very close to the middle of that growth stage, and a little data after. And then we'd be able to extrapolate to say, okay, plot 102 had not reached match head square 38 days. It was past it at 42 days, so we're pretty confident it was there at about 41 days. We've really tightened. I mean, we're talking about plus or minus a few hours. We feel pretty confident that we've been able to capture when each plot reached a given growth stage. So here's the data. This is the 2018 data. Each line represents the average of a variety within a given location. Tremendous amount of variability here. And I'm gonna separate location and variety and make a couple of initial observations. We're looking at days after planting. And I just want to share with you, the power of this potential data set. All right. Number one, we had tremendous variability from location to location. So you look at the days required to reach any given growth stage. We're ranging anywhere from about 35 days to reach square after planting to close to 50 days after planting to reach square. This just looking at days after planting. Now, if we use heat units, absolutely, we're going to tighten this up because heat units would be an actual measure of the environment. Days is just a measure of time, right? This magnitude is absolutely a function of environment. And environment, you'll see in the next slide, is going to be the dominant factor in growth stage as opposed to cultivar. The other point I want to make, look at the variability we see around cutout. Of all the growth stages that we're measuring, cutout is going to be the one that is most dependent upon the environment, right? If we get stress, whatever stress it may be, cutout's going to be the one that we're really going to see the variability in. And I think if we're trying to predict yield, which at this point we're just at growth stage, but if we're going to predict yield, we probably need to spend more time on that cutout prediction. Now this is not looking at location, this is looking at cultivar. Location here, averaged across cultivar. Cultivar, average across location. Look at how tight these lines are. Delta Pine 1612 is going to be the lowest. 1646 is right there in the middle. And the highest is 1851. We're seeing separation. It's very, very slight differences, very significant differences. We're seeing separation in these varieties. While it does not mean much early on, we're talking about maybe a day or two in the time it takes to reach square. By the end of the season, we're talking about 7 to 10 days difference in maturity between something like Delta Pine 1612 to something like 1851, right? We're not talking about 20 days like we're seeing on location. Very small differences, but consistent differences that we're seeing with cultivar. Now this is the only DD60 data I want to share with you. This is data from Tennessee, so I've not worked with a climatologist on this. I pulled this myself. This is going to be days after planting on this top, accumulated heat units on the bottom, and then you can see our growth stages again running across the bottom. I want to start by looking at graphed across cultivar, so just looking at location. Days after planting, it was a hot start to the year. Both years that we had this trial, we had a hot start. We came out of the ground and we reached all growth stages, beginning at square, reached all growth stages before our standard guidelines. And these guidelines that I'm referring to, the lower here and the upper here, would have been established by Hutmacher in 2002. It's about the most recent evaluation of the DD60 guidelines that we have. So not only are we reaching square faster from a days after planting standpoint, we're continually reaching growth stages quicker than we should. Notice the significant break here in trend line going from cracked bowl to 60% open. This is one of the real interesting parts of this data. We're seeing maturity at the end of the year much faster than we have typically seen, traditionally seen, when we developed these guidelines initially. From a DD,
What did you mean with that? You saw maturity sooner at the end of the year. I didn't understand.
So what we would typically expect with this trend line to hold steady. So we would expect to see that variability there to be consistent from time frame to time frame, right? So it's taken far fewer days after planting to reach that 60% open than the guidelines that were established by Hutmacher.
Okay.
In addition to that, it's taken fewer heat units. So early in the year, it was hot. We were accumulating a lot of heat units early. We jumped above both trend lines, the lower and upper thresholds from what Hutmacher had published. But notice how at the end of the year, we crashed back within those, right, again. So we're moving from crack to 60% open faster. Those bowls appear to be maturing more quickly at the end of the year. I'm thinking that 60 lower threshold may need to be adjusted on the end of the season. All right, so I've talked about some more academic approaches to trying to reevaluate this. I want to give you one very practical deliverable that you'll see in the next couple of months. We've partnered with the North Carolina State University Climatology Office. Dr. Guy Collins and Keith Edmonston developed this cotton planting conditions calculator a couple years ago. Works extremely well, and they're basically pulling GHCN data to predict growth state, to predict planting conditions over the next 5 days. He approached their office on developing a DD60 calculator. At the moment, Eric, if I'm going to get DD60s, I got to calculate it by myself, right? We don't have a whole lot of access to. There was one website, and it's now down as far as reporting DD60s in the Mid-South. NC State's going to develop a calculator for us. You put your field location in using that same Google Map template that they did the planting conditions calculator with. You put your planting date in, you put your location in, and it'll calculate heat units to the current date from that time frame. I think that'll be a tremendous value. In addition to that, we're going to have, if you put last effective flower date in there, and you want to see heat units accumulated, this end of season, when do we terminate insecticide use? A lot of potential savings there. This calculator should be set up to where you put your field in, you put that last effective bloom date in, and it should tell you at which point you should be able to cut off those insecticide applications and save some money there.
Is the temperature based on weather station, or are they modeling temperature at a given location?
It's going to be extrapolated based on NOAA weather data, GHCN weather station. So I'm sure it's not going. They're not going to have a weather station within a given location. It's going to be extrapolated across that landscape. A lot of power there. Very easy to use, and I think we're going to see a lot of utility out of that. I'm going to have a report updating our thoughts on this DD60 guideline system, and potentially having a new way to model plant growth and development. And a lot of those guidelines will likely be embedded at some point in that North Carolina State University calculator. Extremely excited about this data set. I don't think we've had an opportunity, even when the DD60 model was initially developed, we had a couple of data sets from across the belt. We didn't have a concerted effort to compile this much data with such a rigorous protocol. So we're very excited for Cotton Incorporated taking the reins to help us get this data collected. I think I've got just a few minutes for questions.
With that last calculator, did I understand you right to say, essentially, you could take a field, put in your NAWF, and from that you would get a projection or probability or something of when?
You probably get a 30-year average probability, and then it would give you where you stand at the moment from temperature accrued since that date.
And I'm assuming now it probably doesn't take into account varieties, whether they're early, mid, or late, but it would.
That it could potentially, right? And so we could say, based on relatively from the 1612 to 1851, we would expect plus or minus 3 days.
But is that shooting from planting till projected, or is that, can it be no above white flower 5?
Hopefully it'll be both. Hopefully it'll be both. So, you know, in July, you're trying to figure out where you stand compared to what you had last year. You put in that planting day. If you're in August or September and you want to know, then you put that no above white flower 5 date in. A lot of utility there. And it's excited to have the team at North Carolina State University working with us because, I mean, they know what they're doing.
Well, are we going to drop a possible pin, or are we going to have to load boundaries in like?
It'll be pin based. So from my understanding of the way that they're doing the calculation, that pin would give you as much value as if you were to draw the entire field boundary. Yep. And that planting conditions calculator is very easy to find, and it works very well. One of the interesting things is they didn't put boundaries on it. So if you want to see planting conditions in Puerto Rico, you can do that. You can put it in the middle of the Atlantic Ocean. And anyway, so it's a really neat calculator. And I'll tell you, it works really well. We watched it in May here, and we've been watching it for the past couple of years across the belt. It does a really good job. Rainfall prediction is included in that, and that just to tell you how good they are. The rainfall prediction is included in that calculator. So if there's a chance of over half an inch over the coming 5 days, they'll drop conditions down to 4 margin as opposed to good to recommend.
How do you measure the temperature? Temperature, this is you said the registration temperature?
Yeah, so this would be NOAA measured temperature. This won't, we're not measuring soil temperature. This would be reported from a.
Is it all weather stations were in the same field that you make measurement?
So we've approached DTON to allow him to create the data set, create the temperature data set. The data that I've reported was from a base station that was about 100 yards from the field.
I work on weather stations. If you install the weather stations 1 feet or 2 feet higher,
Right.
the temperature is different.
So do you have confidence in the NOAA
Yeah.
system? I mean, that's, I don't, Dr. Espinosa is shaking his head. We're assuming that the NOAA system is going to be good enough, accurate enough to predict.
It's better than whatever.
Yeah.
For temperature, it's really good.
Yeah.
That grid, it's probably using their gridded product, so that's why you can drop a pin and get it anywhere.
So the resolution is what, like 5
Kilometer
kilometers?
maybe?
Five?
Yeah, maybe 4 kilometer maybe, I think.
Actually, we could use it for any crop, I guess.
Yeah,
Yeah.
absolutely. Yeah.
No, it won't work for any other crop.
The
Well,
only
Tyson, this is just more of a question about why, other than understanding that yes, our technology is advanced and yeah, better weather data definitely makes sense to reevaluate and use the tools we have available now that we didn't then. But have things also changed, I guess, with the genetics and the varieties? Why, not saying from like crack bowl to 60%, it's happening so much quicker? Do you think, or what do you think?
I'm going to defer to Dr. Borland. What are your observations? Would you disagree with some of these trends that we're seeing?
No. I think there's, that's been one of my pet ideas I've been wanting to look at for a long time, because I think there's some real differences there. The thing that really confounds it is bow load. And
Right.
that can change that whole dynamics going up the top of the plant. I really applaud what you're doing here with these thresholds. That's something that Derek and I have talked about many years, and neither one of us had the ability to do it. So, but it's always been curious to me. You're a physiologist. You can answer this. Why do they pick out 86 as this optimum high for cotton? That just happens to coincide with 30 degrees centigrade. Is there a coincidence there? Or is that? Is there a reason?
I defer to our physiologist in the room.
Honestly, I had the same question when we were discussing corn, because we had to set up an experiment and we searched everywhere why that 10 degrees Celsius came from where
Yeah.
when we set up base temperature.
It's a nice even number, I
I think
think.
that's the reason.
Yeah.
Well, I think I have a theory on that, though. If you look at what's the optimal temperature for cotton is between 28 and 30 degrees, and you go to Arizona, it will try to cool itself to 28 or 30 degrees
Yeah.
C. And so they're putting in an artificial upper threshold. In reality, under well-watered conditions, a cotton crop in Arizona will never see much above 30 degrees C, even though it might be 45 degrees C. So that, I think that's a
To
playing
cover
into
most
it.
environments.
Yeah.
But I always thought that was curious. One other real quick question. I noticed that on your no buff white flower, why you did that was counted 10 consecutive, or you looked at, you
So-
did it until you found 10 consecutive plants at 5.
No, so
Or less.
our
I
recommendation,
misunderstand.
well, for the protocol, we said you need to measure 10 consecutive plants for every growth stage. So for the note above white flower 5, we wanted 5 of those 10 consecutive plants to have reached note above white flower 5.
I see.
So theoretically,
I misread
yeah.
it.
So
I'm sorry.
they could have either measured and basically we're getting an average of cutout per plot.
I read it as you had to have 10 consecutive
No, sir.
plants.
No, sir.
Fine, you don't have a problem.
Yes, sir. Yeah,
Okay.
yeah. Back, Dr. Kelly, back to your comment. So, in this speeding up from crack to 60% open, I think part of what we're seeing is better first position fruit retention. I mean, absolutely from what we saw in 83 till now. Better first position fruit retention. So we've got more fruit lower on the plant. And I think part of this is a response of the plant to a boll load. So when we have a tremendous load on that plant, I think it's more focused on completing that fruiting cycle than it would be if we had fewer fruiting positions. And I don't have any physiological data to back it up.
Oh, you're absolutely right.
That's what I'm seeing. Yeah,
Since you and I both agree on that, it's gotta be right, right?
it's absolutely